Hey everyone, welcome to Trigonometry. This is going to be lecture 1 of the course. And in this section we're going to start at the very beginning of trigonometry. We're going to start with a discussion of what angles are, and we're also going to get into degree and radian measure, right? Degrees, many people have heard of the degrees and the idea of degrees as representing the measure of an angle, but radians will be something that, unless you've taken trigonometry before, or maybe you've taken some calculus courses, you'll probably not have seen radians. So we'll get into that as well in this section. Okay, so let's go ahead and get started. And again, I'm going to call this lecture 1, angles and radian measure. Okay. And something to note, many books will start kind of the introductory section of trigonometry with angles, arc length, and circular motion. We will be discussing arc length a bit here, but the circular motion piece we'll leave off for now. We're going to focus on angles and the measure of angles, and we'll talk a little bit about arc length. So let's start with, what do we mean by an angle? Okay, and so given a point V, which we'll label it V, but V here in this context stands for vertex. So given a point V, the vertex, we can extend a line called a ray, right? So I can draw a line off of this point V. We can extend a line, which we'll call a ray. So I'm kind of tossing in some vocabulary here and there, right? So given a point V, which is also known as the vertex, we can extend a line called a ray. Okay. Now, when two rays, we'll say, extend from a common vertex, they form what's called an angle. Okay. So when two rays are extended from a common vertex, they form an angle. Okay, so they form an angle. And the angle is really the space between the two rays. Okay, so it's going to be this thing here. So this is, we'll call this ray 1. And we'll call this one up here, this is ray number 2. Right, and in between them, this thing here, this is the angle. Okay, so again, just kind of, starting from the very beginning, getting some of these ideas down from the very, very beginning. Okay, now we call one of the rays the initial side, and the other ray we call the terminal side. So we call one of the rays the initial side, and the other ray we call the terminal side. Okay, and so if I say this is the initial side, right, then maybe this other ray up here is the terminal side. Right, and it does matter which one you call which, because the orientation of the angle is from the initial side to the terminal side. Right, so the angle moves from the initial side, to the terminal side. Okay, and so it does matter which you call initial and which you call terminal. And the reason it matters is because the direction of the rotation is going to indicate whether the angle is positive or negative. So the direction, the direction of the rotation, right? The direction of the rotation indicates whether the angle is positive or negative. Okay, so positive or negative. And so let's start with positive angles. Okay, positive angles have counterclockwise rotation. Counterclockwise rotation. Okay, so what that basically means is really what we've been drawing. The angles move counterclockwise, right? So they would move around a clock backwards. Okay, so this is our V and our ray A and ray B. This is our angle. Okay. Okay, and this would be an example of a positive rotation. Let's see another example. So maybe I got my V here, my initial side there, and my terminal side is over somewhere like this. Again, this is another example of a positive angle because of the rotation. Okay, a negative rotation is going to involve clockwise rotation. A negative angle will have clockwise rotation. So we haven't really drawn one of these yet, but let's take this example. There's my V, there's ray A and ray B. Now let's say instead of rotating from A to B counterclockwise, the rotation goes the other direction. Right, so to get from A to B, you would have to start at A and rotate all the way around like this. And so this would be your angle here. Right, this is an example of negative this is a negative angle because the rotation is clockwise. Okay, another example be something just like this, right, where the angle again moves clockwise, right, but in this case it just moves down a little bit. Okay. All right, so that is that's kind of an introduction to angles, right? So you've got two rays that begin at a common vertex, and the rotation from one angle, from one ray, the initial side, to the other ray, the terminal side, that's going to map out your angle, right? And angles can be positive or negative depending on the orientation of the rotation. Right, so positive angles have a counterclockwise rotation, and negative angles have a clockwise rotation. Okay, now you'll notice here I'm denoting angles with the word angle. Right, that's not how we want to do it going forward. Right, so the convention in trigonometry with regard to angles is to denote them using lowercase Greek letters. So we typically use lowercase Greek letters to indicate an angle. Okay, and so the most common ones are this shape here, which is alpha, and then beta, which is kind of like a B. I have kind of a goofy beta. You'll see other examples. If you read your textbook and look at some of the notation, the betas look a little different, but you can think of it just like a big kind of goofy B. All right, so maybe more like a B, but with a weird thing on the end. And then I think the one that's most common is theta. Okay, so theta, alpha, beta, and theta are the most common. There's also gamma. You might see gamma sometimes as well. Right? Those are how we typically will denote angles, right? So we might say something like this. Might denote it like this. So you've got your vertex, you've got ray A, ray B, and angle alpha. Or, vertex V, ray A, ray B, and angle theta. So this is the kind of notation you can expect. And then later, when we get into the trigonometric functions, you'll see things like sine of theta, or sine of alpha, or the tangent of gamma, or the cosine of beta, etc. So this is all just notation, right? And so the idea here is that the angles, we frequently use these lowercase Greek letters to set them apart from other symbols that are used more commonly in algebra, like lowercase a, b, more like English characters. Okay. All right, so those are angles, and that's how we frequently will notate them. The next idea that is really important is the idea of the standard position of an angle. So an angle is said to be in standard position. Okay, it's said to be in standard position if its vertex is at the origin. It's at the origin, and its initial side is positioned on the x-axis, on the positive x-axis. So its initial side is positioned along the x-axis, along the positive x-axis. Very important. Okay, so for example, if I have my y-axis here, and I have my x-axis here, right? So this is the origin, right? This is 0, 0 in the Cartesian coordinate system, the Cartesian plane. 0, 0 is the intersection of the x and y axis. The positive x-axis is this section over here, okay? And so maybe I have some ray, I'm gonna darken it here, some ray coming out of the origin along the positive x-axis, and I have some other ray up here somewhere, right? And so then there's this angle alpha between those two. Then this angle would be in standard position. Okay, right? It's in standard position. The vertex is at the origin, and the initial side, which you see here, is along the positive x-axis. Now, to contrast, right, maybe I again have my y-axis and my x-axis, and I could have maybe the same angle, but you can see that it's moved up somewhat, right? It's in a different position, right? So here, this thing here, which we'll call A, maybe it lives here now. Okay, and then this thing here, which we'll call ray B, it's up here. So it's like you took the whole thing and just kind of went, moved it up, right? So this is standard position. And this over here is not standard position. Right? Now, the origin, the vertex is still at the origin, 0, 0, but the initial side, A, is not along the x-axis, the positive x-axis. Right? So this is not in standard position. Okay. All right, so this will become important when we get into the trig functions, and so we got to make sure we address all of these items. All right, so a lot of this lecture is going to be just kind of terminology and conventions. All right, kind of getting used to some things. Okay. All right. So the next idea here is, this is kind of a simple idea. It's just a classification system, but we say that when an angle theta is in standard position, so when an angle theta is in standard position, really two possibilities can exist. So when an angle theta is in standard position, then either the terminal side will lie in a quadrant, or will lie on an axis. All right, that's just kind of common sense, right? So I've got my XY coordinate system here, right? And my angle's in standard position, right? So my initial side is here, my vertex is at the origin. Then I can either have my angle lie inside of a quadrant, like quadrant 1, or maybe quadrant 2, or quadrant 3, or I can have it lie between quadrants on an axis, right? So it can either be, you can have something like this, right? So here's alpha. This would be an example of lying in a quadrant. Alpha is in a quadrant, right? And in this case, it's in quadrant 1. Okay. Another example would be, I've got my X and Y axis here, my initial side, we're in standard position, and maybe my terminal side is down there, right? And so in this case, again, alpha is in a quadrant. This time it's quadrant 3. Okay, all right, and so this is the first option, right? So in this case, the terminal side lies in a quadrant. The other option is that it will lie on an axis, right? And so you can contrast this with this scenario like this, where, again, your XY axes, and you've got a vertex, you're in standard position, so your initial side is on the positive x-axis, and your terminal side is also on an axis. All right, so in this case, alpha lies on an axis. So in this case, alpha lies on an axis. Now, when that happens, when you have a situation like this where the terminal side of an angle in standard position is on an axis, then we call that angle a quadrantial angle. So quadrantial angle. Okay, so kind of a strange term. And again, this term isn't super important. I just want to make you aware of it in case it comes up later. You might come across example problems that speak of quadrantial angles and such. And so I just want to make sure you're familiar with that. So another example would be something like this, where you've got your initial side along the x-axis here, and maybe your terminal side is over here, right? So your angle alpha, it looks like this. So again, quadrantial angle. Right? Right, so your angle can either lie in a quadrant or it can be quadrantial. Okay. All right, very good. Okay, so that's sort of the introduction to angles. Okay, and now what we want to do is kind of move on to how we determine the measure of angles. So a little bit of background here. Angles are basically used to determine, you can kind of think of it like this. Angles are used to determine the amount of rotation needed for the initial side to coincide with the terminal side. So angles are used to determine the amount of rotation needed for the initial side to coincide with the terminal side. Okay, so that's really the idea with angles, right? And so, you know, if I have, again, I'll redraw another angle here. So if I have my initial side A, and then I've got a terminal side B, then the angle between A and B, alpha is a measure of how much I have to rotate A until it lies on top of B. Right? That's how you can think of it. It's a measure of the rotation needed to bring A on top of onto B, right? Right? Clearly I can rotate A up until it lies directly on top of B, and you can't tell the difference between the two. And how much I have to do, how much I have to rotate A to accomplish that is given. That's what alpha tells you. That's what that angle alpha tells you. How much do I need to rotate A until it's right on top of B? Okay. And so there's a couple of commonly used measures for angles. So there's two of them. The two commonly used measures for angles are, the first one, degrees. Bad handwriting. The two commonly used measures for angles are degrees, which most people have probably heard of, and radians, which most people have probably not heard of. Okay, so the two commonly used measures for angles are degrees and radians. And so because people are more familiar with degrees, we'll start with degrees, and then we'll develop some intuition with regard to degrees, and then we'll contrast that with radians. Okay, so with degrees, so when in the degree measure, a complete rotation all the way around in a complete circle is 360 degrees. So a complete rotation is 360 degrees, right? And so if you think about an angle in standard position, a complete rotation means you start with the initial side at the positive x-axis and you go around until you're right back on top of yourself. And so that's 360 degrees. Okay. And so that being said, then a half rotation is half of that, which is 180 degrees. Okay, so if my initial side is over here, again on the positive x-axis, and I rotate halfway around the circle, that's a rotation of 180 degrees. 180 degrees. Right, and then the other angles kind of in between would be 90 degrees and 270 degrees. Right, so, something like this, 90 degrees. This is also called a right angle. It's also called a right angle. And then you've got 270 degrees, which would be like that. Right, and then everything in between. Okay, everything in between, right? So you could think of angles that are less than 90 degrees, like maybe you got something like right in the middle, like that, and maybe that's 45 degrees. Okay. Okay, and so this is the degree measure. So most people, I think, will probably have heard of this. Maybe they don't have all the details with regard to degrees, but they'll have heard of 90-degree angle or something, or maybe they'll know that if complete rotation is 360 degrees, half rotation is 180. They might know these things already. This is not uncommon knowledge here. Okay, Now, angles in the reverse direction, as we've seen, are negative, but they're going to follow the same protocol. So angles in the reverse direction will be negative, but follow the same protocol. All right, and so for example, if I have my XY axis here and I rotate like this, that's negative 90 degrees. Right, and so similarly, if I go like this, that's negative 270 degrees. Right, and then obviously the full circle, but in the clockwise, with clockwise rotation, like so, is negative 360 degrees, right? Okay, so as you can see, it's the exact same protocol, but it's just backwards, right? And everything works out fine. Okay. Now, it is possible to rotate beyond 360 degrees. Of course, your terminal side will just land in a position where a smaller angle could represent it in standard position. But as far as the angle goes, angles can be as large or as small as you like, right? So angles can be as small or large as you like, right? So for example, right, if I have my XY coordinate system and I rotate all the way around, that's 360 degrees, but I could keep going, right? So I would have 360 degrees, that got me from here to here, and then another 360 degrees, and that would get me a total of 720 degrees. Right? So this would be an example of an angle that's 720 degrees. Okay. And similarly, you could have something like, maybe I start and I go around once, and then instead of going around a second time, I just go a quarter of a rotation, so just up to here. So that'd be like 360 degrees from here around to here, and then 90 degrees. Right? And so that's going to be a total of 450 degrees. Right? Okay. And then the same idea would exist in the opposite direction as well. Right? I could start here and I could go around 360 degrees in the negative, and then a further 90. Right? And so this would be negative 450 degrees. Right, just because of the orientation, clockwise orientation of the rotation, and versus counterclockwise. Okay, so let's do an example. Right, a key thing that you need to be able to do after this lecture is draw angles. Right, just provide a reasonable drawing of what an angle looks like. So draw each angle. Okay, and I'll give you a couple of examples here. So A, 45 degree angle. B, a negative 90 degree angle. C, a 225 degree angle. And D, a 405 degree angle. Okay, so let's draw these. So A would be, we know that from here to the y-axis would be 90, and 45 is half of 90. And so it must be somewhere in between here. Okay. B, we're looking for a negative 90, right? We've done this example already, right? But if I start here, again, standard position is how we want to draw these. If I start with the positive x-axis, then 90 degrees would be up to here, so negative 90 would be down to here. All right. For C, 225 degrees. So let's think about this. So we know from here to here is 180 degrees. And, you could just do a little side calculation. So 225 minus 180, and you'll see that that's 45. Right, so I need to go 45 degrees more, which would be halfway through this next quadrant. Right, so it'd look like this. So this would be 225 degrees. And so it's 180 degrees plus another 45. So 180 plus 45 is 225. So that's how you can figure that one out. And then D, we're looking for 405 degrees. Okay, so we know that's more than 360, so we're at least going to go around once. All right, so we go around once, we get to here. And then I got to figure out how much further to go. So I could take my 405 and I could subtract 360 from that. Right, and so if I do that, I get 5, and then 40 minus 36 is 4. So another 45 degrees. So that means I got to come up to this halfway point again. Right, and that would be 405 degrees total. Okay, so it's a very simple system to work with. I mean, really, you just need to know that complete rotation is 360 degrees, and then basically everything just kind of falls from that. Half rotation is 180, a quarter is 90, everything in between, right? Kind of everything is positioned relative to that complete rotation of 360 degrees. Okay, very good. So that's degrees. Let's move next to radians. Let's move next to radians. Okay, so radians will be less familiar to people, I would assume. Radian measure. Radians will be less familiar to people, but when it comes to trigonometry, radians are extremely useful, and we'll see why as we go through the course. I won't try to explain it now. I mean, I'll explain what a radian is, but the usefulness of it will become apparent as we start to work with the trig functions. Okay, not to say that degrees aren't okay, they're fine. Radians just they add a simplicity to the trig functions that you can't have with degrees. Okay, and so let's talk about radian measure. Right, so we're going to use this term central angle a lot, and so we need to define it. A central angle. Okay, a central angle is a positive angle. So it's a positive angle whose vertex is at the center of a circle. Okay. All right, and so the rays of a central angle are going to intersect the arc of the circle, right? So if the central angle is at the center of a circle, then any rays that extend from the center are going to intersect an arc. And so let's get a picture going here, right? So let's say I've got my XY coordinates here, and let's try to draw a circle here. Okay, and so my vertex is right in the middle. Right, and so let's say we're in standard position, so one of the legs is here, one of the rays is here, and then let's put the other one up here somewhere. Okay, right, and so we'll call this A, and we'll call that B, and the vertex we'll just call V in case you need to refer to it. Okay, and so the rays of this angle, they intersect the circle, as you can see. They intersect here, and they also intersect here. And so another word for this intersection, this intersecting, is to subtend, right? So we say that the rays of a central angle will subtend, which is just another word for intersect. They'll subtend or intersect an arc of the circle. Right, and so what that means is they'll mark off this arc, right? So remember, to have an angle, you have to have rays, right? And so you've got the first ray here, which is A, you got the second ray here, which is B. They're a central angle, so there's a circle outside there's a circle whose vertex is the vertex of the angle, which is right in the center of the circle. The rays of the angle are going to intersect the circle. Okay? All right. So let's say that the radius of the circle is r. We'll just put a label on it, r, right, for radius. Radius means the distance from the center of the circle to the edge of the circle, right? So this distance here is r. So if the radius of the circle is r and the length of the arc that the rays subtend is also r, right? So if this is r, this distance here, right, this arc, if that length is r as well, then the measure of the angle alpha in this scenario is exactly 1 radian. Okay, so let me write all that down. So if the radius of the circle is r, as I've said here, the radius of the circle is r, and the length of the arc subtended by the central angle is also r. Okay, and the length of the arc subtended, i.e. intersected, I'll put that here, intersected, is also r. Okay, then the measure of the central angle is exactly 1 radian. Okay. All right. And so the 1 radian is an angle sufficient to sweep out an arc whose length is the same as the radius of the circle. Okay? So that's the idea behind radian measure, right? So you've got an angle inside of a circle, right? That angle is naturally going to have some rays, and those rays are going to denote an arc. Okay? And so if the circle has radius r and the arc length is also r, then that angle is 1 radian. Right, now notice if B was a little bit bigger up here, so this will say B prime, that angle from A up to B prime is more than 1 radian, so it's like maybe 1.2 radians or something, right? So alpha is 1 radian, and if we had to go a little further, it'd be more than 1 radian, like 1.2 radians, for example, whatever it happens to be. Okay. Now, we'll see how many radians there are in total within a circle in a moment, and some of the convenience of radian measure will kind of be revealed at that point. But it's important to notice that this works for circles of any radius, right? So for example, let me try to draw a reasonable representation of this idea. Right, so if I've got a XY coordinate system and I've got a vertex at the center, right? And let's say I've got circles of varying radius, right? So this one we'll say has radius 1. Okay, and then I got a bigger circle out here. And I can't promise these will look like circles, but you get the idea, I hope. And maybe it has radius 1 plus 1, so 2 all the way out here. Okay, and then maybe a third circle way out here, whose radius is 1, 2, 3. Right? So I'm kind of denoting it like this. So 1 is the radius from here to here, 2 is the radius from here all the way out to here, and then 3 is the radius from the center all the way out. 1, 2, 3. right? And if I just put in some angle here, alpha, right? And if alpha is exactly 1 radian, then this arc length is 1, this arc length would be 2, and this arc length would be 3, right? So for a circle of radius 1, a central angle with measure 1 radian would subtend an arc of length 1. Okay, and that's what you'd see here. So this is 1, then this angle alpha of 1 radian would subtend an arc of length 1. If for a circle of radius 2, like this middle circle, for a circle of radius 2, the central angle again still 1 radian, it's going to subtend an arc of length 2, right? You see it's the same angle, right? And as the circles get larger, then the arcs grow in coordination with the radius. Okay, and so the same angle can be used for whatever size circle. Okay, so just making sure that that's clear, because it's a common problem. So alpha here is assumed to be 1 radian, right? And so this arc is 1, this arc must be 2 if that's radius 2, this arc must be 3 because that radius is 3. Okay, so that's kind of one of the key ideas. Okay. Okay, let me just write some of that down just to make sure. So for a circle of radius 1, a central angle with measure 1 radian will subtend an arc of length 1. Okay, and I could say the same thing for 2. I'll just replace 1, 1, 1 with 2, 2, 2. Right, and so if r equals 2, the arc length will equal 2. Right, if r is equal to 3, the arc length will equal 3, right? Because radians are, so the length of the arc depends on the radius. If your angle is 1 radian, then the arc length will exactly equal the radius. Okay. All right. Okay. Moving on. So, our first theorem of the course. And we're going to have a bunch of theorems, so don't worry. Don't worry, there'll be plenty of these. So, first theorem. The first theorem is a theorem about arc length, which basically codifies what we just described in a somewhat simpler manner, right? So, for a circle of radius r, okay, so for a circle of radius r, a central angle theta, a central angle theta radians subtends an arc whose length s is, so what is s equal to? So let's draw the picture before I write it. All right, so I've got some circle, radius r, I've got a central angle theta, okay, and then I've got some arc length s. So if I know the radius r and I know the angle theta, I can determine s using the following formula. So s is going to be equal to r times theta. Okay. Right, and so this is the same idea as what we just had before, but it extends it. So naturally, if if theta is equal to 1 radian, then s is equal to r times 1. So s is equal to r. And that's the case we were just talking about, where the radius and the arc are exactly the same, right? And that only happens when theta is equal to 1 radian, right? But if theta is larger than a radian, then the arc length will be longer than the radius. If theta is less than 1 radian, then the arc length will be shorter than the radius, etc. Right? So you can keep going with this idea. All right, let's, I'm going to do a quick proof of this. Not really a proof, but just to give you some sense for where this comes from, right? Some sense for why this might be true. Sometimes proofs are more useful than others, but let's say that we have a circle and we have a radius r, and we've got a theta and an angle s. Okay, and let's say we have another angle, theta prime, we'll say, and another arc length s prime. Okay, so remember, these are the arc lengths. Okay. Now, one of the things this demonstration relies on is the following. So from geometry, we know that theta, this angle here, divided by the other angle, theta prime, is equal to, that ratio is equal to s over s prime. Okay. Okay. So this is a relationship that we know from geometry. Okay. So using this relationship, let's assume for a moment, we'll set up the proportion using it this way. We'll assume that theta prime is 1 radian. Right, so assume this angle theta prime is 1 radian. Okay. From the definition then, right, what definition? Well, from the definition of a radian measure, from the definition, I'll say of radian measure, right, from the definition of radian measure, what does that say about s prime? So if theta prime is 1 radian, and obviously this is r, right? If theta prime is 1 radian, then what does that tell us about s prime? S prime must be equal to the radius of the circle, right? Right? Because if theta prime is a radian, then this must be r. This is r, obviously, and this must be r as well in order for that to be 1 radian. Okay? So that little fact kind of sets it up. So theta over theta prime is equal to s over s prime, right? And if we assume that theta prime is 1 radian, then we get theta over 1, right? The measure is 1 radian, is equal to s over s prime, but s prime, in the case of theta prime being a radian, must be equal to r. Right, so we get that. And then we can do a little bit of reorganization here, and we see that s is equal to theta times r, or r times theta, whichever. I guess I wrote it r times theta up here, but theta times r down here. Same thing, right? Okay, so that's kind of a little demonstration of how this is true. Okay. Okay, and so this is going to be a very useful. This is going to be a very useful little theorem. We're gonna, anytime you need to know the arc length and you know the radius of the circle, you know the angle, you can quickly determine the arc length. Or really, if you know any two of these three quantities, you can always find the third one just using algebra. Let's do an example. Let's see an example. Let's say find the length of the arc find the length of the arc of a circle of radius 2 meters. Right, radius 2 meters, and then subtended by a central angle by a central angle of 0.25 radians. Okay, so find the length of the arc of a circle of radius 2 meters, subtended by a central angle of 0.25 radians. All right, so we're looking for the length of the arc, so we need S, right? And we know that S is equal to R times theta. We're told R is 2 meters, and theta is 0.25 radians. Okay, and so I can easily multiply those together, and I get 0.5 meters. Right, and so what does that mean? Well, if I've got my initial side and I've got my terminal side, and this is theta, where theta is equal to 0.25 radians, then this arc length here, well, and so assume the radius here is 2 meters, then this arc length here is 0.5 meters. Right, that's what we've just figured out here. Okay. Very good, very good. All right. One more example here. Let's say if an arc has length 30, here we're going to kind of scramble up the information a bit. So if an arc has length 30 feet and the radius is 15 feet, what is the radian measure of the central angle? What is the radian measure of the central angle? Well, you know, I mean, we know that S is equal to R times theta, right? We're told S, we're told R, what we need to know is theta. Right, so we can just do a little algebra here. If S equals R times theta, then S divided by R is equal to theta. Right, so the length of the arc divided by the radius is equal to the radian measure of the angle, the central angle. Right, and so we could easily do that. So theta is equal to S over R. We're told S is 30 feet and R is 15 feet. So that means theta must be 2 radians. Right, so 2 radians, and that makes sense, right? Because the arc is twice the length of the radius. Right, so that would mean the central angle must have swept out exactly 2 full radians. If it had swept out 1 radian, the S would be 15. It swept out 30, so theta must be 2. Must be twice as big as 1. Okay, very good, very good. Okay, so that's the idea with radians. Okay, and it'll take a while. It'll take a couple of weeks, I would say, before you start to feel comfortable with the idea of radians. One of the ways you'll get comfortable thinking about things in terms of radian is getting comfortable with the idea of converting between degrees and radians. And so that's what we want to talk about next, converting between degrees and radians. Right, we want to be able to convert between these. Now, many of you will feel very comfortable with degrees. You'll have used degrees over, previously, and so you'll feel comfortable with them. You'll be used to that way of thinking. We want to get you to start thinking about angles in terms of radians because, again, the value there's a value add for trigonometry to think of things in terms of radians. And so the best way to do that is to start converting common angles that you're familiar with, like 90 degrees, converting those to radians, right? Start thinking about what 90 degrees is in radians, right? And so the way we usually kind of set this up is we start with what we know, right? We know that the circumference of a circle has a certain formula. The circumference of a circle is equal to 2 times pi times the radius. right? So this is a formula you've probably seen in algebra class, right? But if I have a circle and I know the radius, I can determine the circumference, i.e. the distance around the circle, using this formula. Basically multiply r times 2 times pi, pi being the transcendental number 3.14159 ... right? So this is the first formula we need, right? And so an example here would be if a circle has radius 10, what is the circumference? Well, the circumference would be equal to 2 times pi times r. We know r, so it's 2 times pi times 10, so it's 20 pi. And that's approximately 20 times 3.14. You can think of it like that, so 20 pi. Okay. So we've got this formula for the circumference. We just learned another formula. And that is that S equals theta times r, or r times theta, however you prefer to think of it. Right, where S is the arc length. Okay, S is the arc length, right? So we've been kind of thinking about it like this, right? If I've got my r, I've got my theta, you know, and then this is my S, right? This distance here. Now, so these two formulas, when you put them together, can reveal the connection between degrees and radians pretty easily. Okay, and so we've been thinking about the second formula in terms of something like this, but what if instead we think about it like this? Let's say I have my circle, right, and here's my radius right here. Okay, let's say my angle goes all the way around, right? So then the arc that I've subtended is actually the full circumference of the circle, right? So S would be from here all the way around, wouldn't it? S would be the entire circumference of the circle, right? So if the angle theta is like 360 degrees, then S is the full circumference. Okay. Does that make sense? Hopefully that makes sense, right? If you go all the way around the circle, then the arc you're talking about is really the full circumference of the circle. Okay. And so that connection allows us to equate these two. So in the case of theta being 360 degrees, then S is equal to C. They're the same. So in the case of theta equals 360 degrees, S equals C. The circumference is the same as the arc, right? And so that means that theta times r is equal to 2 pi r. Now remember, theta in this case is 360 degrees, so 360 degrees times r is equal to 2 pi r. Right? Now I've got an r on both sides, so I can divide by r on both sides. And so that means 360 degrees is equal to 2 pi radians. Okay. And so that's the connection between these two measures. Right, so the full rotation of the angle with a complete revolution, 360 degrees, is equal to 2 pi radians. Okay, so that's kind of the key. So 360 degrees equals 2 pi radians. So a complete 360 degree rotation is 2 times pi radians. Okay, and using this fact, you can figure out what everything else is, right? So a half rotation, i.e. 180 degrees, is pi radians, right? You just divide 2 pi by 2. Okay, so that's how you get the half rotation. Okay, and you could figure out the others, right? Right, and so really, here's the kind of, usually when you want to convert from one system to another, you have to have a factor. There's got to be some kind of a conversion factor, right? So what do we know? We know that 1 is equal to 360 degrees divided by 2 pi radians. Right, they're the same. 360 degrees and 2 pi radians, we now know, are equal. They mean the same thing. Okay, and so it doesn't matter if I write it like this, or maybe more conveniently, I could write it as 180 degrees over pi radians. I could also flip it upside down. I could say 2 pi radians over 360 degrees, or I could say pi radians over 180 degrees. Right? These are all equal to 1. So this is the conversion factor for degrees and radians. These are the conversion factors for degrees and radians. I always tell people to remember this one and this one. You don't need the other two. These are the most convenient ones to use. 180 degrees over pi radians and pi radians over 180 degrees. Okay, so theorem. And we really did already prove this. We've derived it, so this is where we've seen where this comes from, so now I'm just going to state it succinctly. So to convert from degrees to radians, we multiply by pi over 180. Okay, and then to convert from radians to degrees, we multiply by the reverse, 180 over pi degrees. Okay, so if I'm given an angle in degrees and I want to convert it to radians, I simply multiply my angle by pi over 180. If I'm given an angle in radians and I'd like to convert it to degrees, I multiply by 180 over pi. Okay, let's do some examples here. Okay, let's do some examples. Let's convert each angle from degrees to radians. Okay, and let's have a couple of them. Let's say 60 degrees, 150 degrees, negative 45 degrees, and 107 degrees. Let's do these four. So for A, I want to convert 60 degrees. I want to know what the radian equivalent to 60 degrees is. And so I'd start with 60 degrees, and I'd multiply it times the appropriate conversion. So I'm starting in degrees and going to radians. So to convert from degrees to radians, we multiply by pi over 180. Like so. Right, and so this is 60 pi over 180, and 60 and 180, you can divide that down, and 60 over 180 is basically 1/3. So this becomes pi over 3 radians. Now, when we're talking radians, what we'd like to do is leave the pi in the expression when it's possible to do so, right? Because if I divide this down, if I take 3.14159 and I divide it by 3, I get an approximation, right? So for radians, we'd like to leave the pi in the expression whenever possible. Sometimes it's not possible because you're not told the angle in pi, or in radians involving the value pi. Sometimes you're given an approximation, you can't do anything about it. But if you have the option to leave the pi in, it's always best to do so. Okay, and so part B, we want to convert 150 degrees. So again, just multiply by pi over 180. So I have 150 pi over 180. Right, I can divide that all down by, let's see, 30? Yeah, 30. And when I do that, I get 5 pi over 6 radians. So very simple, right? It's just a multiplication and a simplification. What about the negative 45 degrees? Same problem, no difference. Again, multiply by pi over 180. And so I get negative 45 pi over 180. And I can simplify that down. Divide by what? Well, it divides down into 45 goes into 180 4 times. So this would be negative pi over 4. Okay, radians. All right. So these are all nice fractions. What about D, 107 degrees? All right, if I have 107 degrees and I multiply it, and I want to convert that to radians, I need to again multiply by pi over 180. Right, and in this case I get 107 pi over 180, right? So that's an exact value, but it's not very nice to look at. And so this would be an example where maybe it's appropriate to just divide this all out. So 107 times pi is 107 times 3.14 divided by 180. You get approximately 1.868 radians. Okay. It's fine to leave it as 107 pi over 180, but you know, sometimes the ratios aren't that nice. These are all nice fractions. This one is a little unwieldy, so maybe the decimal's better. Okay, and so that's converting from angles, converting angles from degrees to radians. And so we can do the reverse operation. Let's do an example there. So let's convert each angle from radians to degrees. Okay, and so again, let's say we have pi over 6 radians, and then for B we have 3 pi over 2 radians, and then for C we have negative 7 pi over 4 radians, and then for D we'll say we just have 3 radians. And so no pi in that one. Let's see how these all work out. So for part A, we want to convert pi over 6 radians to degrees, right? So we would take our radian degree, pi over 6, and we would multiply it by 180 degrees over pi. All right, so kind of an easy way to think of this is that if you're given an angle in radians, you basically want to end up canceling out the pi if you can. And so that's how you can remember to go from radians to degrees. It's 180 over pi, because the pi will be in the denominator. Here the pi is in the numerator. They'll cancel. Right? And so what you get is 180 over 6, whatever that is, degrees. And so you can see that's 30 degrees. Okay, so it's just a simple thing. The pi's cancel, right? You can see that. Okay, what about the second one? 3 pi over 2. 3 pi over 2, not 6. If I want to convert from radians to degrees, again, I multiply by 180 degrees over pi. Pi's will cancel, and I get 3 times 180 over 2, and that's degrees. And so you have to do a little bit of math there, but you'll see that this is 3 times 90, which is 270. Okay. What about the negative? Nothing too tricky there, right? So I can just say negative 7 pi over 4 times 180 degrees over pi, 4. Pi's will cancel, and I get negative 7 times 180 over 4. That's the degrees. And this one would be, let's see, so 180 by 4. Well, so you would get basically about, let's see, what, negative 315 degrees. Okay. Right, you can just do the math to confirm that. And then the last one, 3 radians, right? So 3 radians. Right? So there's no pi here, right? So that means it's gonna be an approximation, right? And so what you can do then is you can just take the 3 and you multiply it again times 180 degrees over pi. Right, now in this case the pi doesn't cancel, so you're going to end up with 3 times 180 over pi, and then that's all degrees, right? But normally you don't want to present an angle in degrees with a transcendental number. It's best to approximate here, right? And so if you pull out a calculator and you take 3 times 180 and then you divide that result by 3.14, you'll get approximately 171.89 degrees. Okay, and so that's converting from radians to degrees. Okay. All right, so I think that's where we'll end this lecture. And then next time we'll get into something called right triangle trigonometry. Okay, we'll introduce the trigonometric functions through right triangle trigonometry. All right, I think we'll end it there. Take care. Talk to you later.